ladies and gentlemen. We're going to do the second part of 9.1. Today we're going to just be doing more work with sequences. Our objectives are that we are going to continue setting the foundations of our sequences. So what I want to talk about today as we start is pattern recognition for sequences. So this, in my opinion, is one of the hardest things for me, but it can be doable if we decide to make some choices and show a lot of our work as we try to figure out our sequences. So I'm just going to start with an example. So I want to find a sequence, and we're going to call our sequence A sub n, whose first five terms are, and it's going to be 2 over 1, 4 over 3, 8 over 5, 16 over 7, and 32 over 9. And then I want to determine, sorry, brain and mouth, haven't had enough coffee this morning. I want to determine convergence. And what I mean by convergence is, does the sequence converge? Does it diverge? And if it does converge, what would it converge to? Alrighty, so if you look at the sequence that we have here, we notice that the numerator is going to be properties of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. Okay, so it's going to be 2 to the n, right? And then the denominator is a little bit harder, I believe, and then it is the sequence of odd positive integers. So one of the ways that I could write an equation for that would be 2 times n, its position, minus 1. So if I verify that, this position is 1, so 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. So then I would actually get the terms of my sequence. Okay, so my rule, A sub n, my parentheses thingies just keep getting worse, is going to be 2 to the n over 2 times n minus 1. Well, then if I want to determine my convergence, I'm going to take the limit. So the limit as n approaches infinity of 2 to the n over 2n minus 1. Okay, and I can notice that if I use direct substitution, I get 2 to the infinity, which is infinity, and 2 times infinity is still infinity. So this is the indeterminate form, and I can use L'Hopital's rule. Okay, so I'm going to take the derivative of the top and the bottom. So then I'm going to have it's the limit as n approaches infinity. Well, the derivative of this guy is the natural log of 2 times 2 to the n, and then the derivative of the denominator is 2. Okay, so the limit now, I've gotten rid of the indeterminate form, is still going to approach infinity, and so we're going to say, therefore, the limit of a sub n as n approaches infinity is going to equal infinity, which means that the limit doesn't exist. Therefore, a sub n, there's my little therefore a sub n diverges. Okay, so that was pretty easy. Alrighty, so one of the things we have to be really careful with our sequences is not making assumptions, because if we're not given enough information, it's really hard to determine a rule. So there is a great example in the book that shows like 5 different examples of the same sequence. And so the first few numbers would be the same. So then they show that without additional information, you could come up with 5 different rules for the same sequence. So you do want to be careful about making assumptions. Alrighty, as I scoop my paper up, let's do another example. And this one says determine an nth term of the sequence whose first 5 terms are. All right, so we're going to have a negative 2 over 1, and then 8 over 2, and then a negative 26 over 6, 80 over 24, and then a negative 242 over 120. Okay, so the first, and then we're also going to determine convergence. And I am being a little bit lazy because technically I should write determine whether the sequence converges or diverges, and if it converges, find the value. But I don't want to write all that. So the first thing that I notice about the sequence is that the signs are alternating. And that's really easy to pull off, okay? So if my signs are alternating, I can manage that by doing a negative 1 raised to the n. If n is even, the signs are going to be positive. If n is odd, then the signs are going to be negative. Well, it appears that the numerators are going to be 3 raised to the n minus 1. And this would be a stretch for me. I would have to work hard to come up with this. Alrighty, so if I notice this is 3 to the first, and then I take away 1, I get 2. And I'm ignoring the signs because this manages the signs. Well, if this is the second term, 3 to the second is 9, minus 1 is 8. 3 to the third is 27, minus 1 is 26. So that means that our rule works for the numerator. Okay, and if I scoot this up just a little bit, so now I want to write out what's happening with the denominators so that we can look at it. Okay, so if I do that, and I'm just going to rewrite our sequence so we have it handy, and then I had 8 over 2, can you see it? Almost. And then I had a negative 26 over 6, I had 80 over 24, and a negative 242 over 120. So let's talk about the denominators. 1 is equal to 1. 2 is equal to 1 times 2. 6 is equal to 1 times 2 times 3. And so you should be kind of understanding the pattern that's developing. 24 is 1 times 2 times 3 times 4, because this is 12 times 2 is 24. And then 120 would be 1, 2, 3, 4, and 5. So then that means that my denominator is actually n factorial, okay? And remember, we've talked about factorials in previous courses, so I'm not going to re-talk about that now. But now I know how to manage my signs. I know the numerator and the denominator, so the rule for my sequence, or for generating the nth term, is going to be a negative 1 to the n times 3 to the n minus 1 divided by n factorial. So with the sequences that we're going to be doing in our course, sometimes it's really nice to write information out because then that helps us to see what we're looking at. Alrighty, so this actually brings up an interesting situation about our alternating signs. Okay, so because of the alternating signs, I know that the limit as n approaches infinity of the absolute value of a sub n would equal the limit of 3 to the n minus 1. Notice that I took away, as n approaches infinity, I took away my alternating signs. Well, if I take away the alternating signs, then the limit is 0. Okay, so then another thing that we need to remember is that factorials grow faster than exponential functions, which means that this number is getting bigger than this number. This will always be bigger, which means that my limit is approaching 0. And so then we have this handy-dandy rule that says for the sequence, and I have a sub n, okay, it's going to converge to 0. And if we can manage the absolute value, then we can talk about what happens. All right, so another vocabulary word that I want to bring in for today is monotonic. And we've talked about this for the last couple of years, but now we're going to talk about it in terms of a sequence. So a monotonic sequence means that the sequence is either strictly increasing or strictly decreasing. Okay, it doesn't change, it doesn't go from increasing to decreasing. It has to either be all of one or the other. Okay, and so then we're going to put this information in terms of a sequence. So I'm going to say A sub n is strictly monotonic if the first term is less than or equal to the second term, which is less than or equal to the third term, etc., is less than a to the n. And if this is true, then this one would be strictly increasing, because it means that the value of the individual terms of the previous term would always be less than the value of the subsequent term. Well, then if I have the opposite situation, 2 is greater than or equal to a sub 3 greater than or equal to a sub n, then we would say that this one is strictly, oops, that's supposed to be a y, decreasing. Okay, so we would say that a monotonic sequence is a sequence that is either strictly increasing or strictly decreasing. So next I want to show you an example of this, and it's kind of entertaining how we're going to get there. So I'm going to have a sequence b sub n, and the rule for that sequence is going to be 2n over 1 plus n. And I want to show that this is strictly monotonic. So this is actually a wee bit of a proof, and it's not horrible, but it does take us a little bit of work to get there. So if I'm trying to show that something is monotonic, I'm going to talk about the first term, and that's going to be 2n over 1 plus n, and I want to show that maybe it's less than, maybe it's greater than, but at this point we're going to choose less than, is going to be less than 2 times n plus 1, and I'll explain this in just a second, times 1 plus n, okay? And this is going to be my next term. Okay, so if you'll notice, if this is the first term, or a term, this is going to be the next term because I added 1 to the numerator and I added 1 to the denominator. So then what I'm going to do is I'm going to manage this portion of my statement. Okay, so what I'm going to do is I am going to cross multiply. Okay, so I'm going to get 2n, and this is 2 plus n, if I simplify my terms, and I'm still trying to show that it's less than 2n plus 2 times n plus 1, okay? So if I expand this side and I expand this side, I get 4n plus 2n squared, still trying to show this relationship. And then if I expand this guy, I get 2n squared plus 4n plus 2. Well, notice that some of my terms cancel, okay? So I get 2n squared goes away, 4n goes away, and then I'll come up here. The resulting statement is that 0 is less than 2, and you're going to say, well, yeah, duh. So that means that because this statement is true, and this term is less than this term, then this is strictly monotonic. And we could even go so far to say that this is strictly increasing, because the previous term is less than the subsequent term. All right, so now we're going to introduce yet again another definition, and we're going to be talking about boundedness. Okay? All right, so I want to talk about a bounded sequence. All right, we would say that a sequence is bounded, so a sub n is bounded, And we're going to say bound above, and I'll show you an example of this in just a second, if there's a real number, and we're going to call that real number m, such that a sub n is less than or equal to m for all n, okay? And then we're going to say that the number m is called an upper bound. Hang on, my computer's doing weird things. Let me get rid of that. Alrighty, here you come back. There we are. The m is called an upper bound. And so here's what it would look like. So I'm underlining the important words. So let's say I have a handy-dandy little sequence, okay, and maybe my sequence, I'm going to draw big dots, does something like this. Then this is going to be the top end, kind of like a horizontal asymptote, and that's going to be the limit of our sequence. And so then this would be bound above, meaning that it's not going to go past that point, and then we would say that the limit, or m, is the upper bound. Okay? Well, then we can say, if we can have an upper bound, then that means we can also have a lower bound, is bound below if there's a real number. We'll call this guy n just so we don't confuse things. N is less than or equal to a sub n for all n, okay? And so then that means that the number n is called a lower bound. So here's what that might look like after I finish writing that really long word. Okay, so let's say I have another sequence, and this guy's going this way, okay? Then maybe I have a lower bound, and so I would say that my particular sequence is bound below. Well, then another weird word that we will see going along with this is the word bounded. And so if you see the expression a sub n is bounded, that means that it is bound above and it is bound below. Okay? And the example that happens to come to mind for me would be that of a logistic function, and I know we're going to have other examples, but that's just what popped into my head. If you think about a logistic function that looks like this, it has an upper boundary and a lower boundary. So if my data had been points instead of a continuous curve, then we would say that that particular sequence is bounded, meaning that it is bound above and bound above. Sorry, bound below and bound above. Okay. Another word that we see would be this, a least upper bound. Okay. All right, so let's say I have a sequence that looks like this, 1 over 2, 2 over 3, 3 over 4, 4 over 5, etc., etc., and then I get n over n plus 1. The least upper bound so that means the smallest lower upper bound, that hurts my head a little bit, is going to be 1. So that means that the numerator will never go below the value 1. So that would be the least upper bound. Alrighty. Then we're going to get, just to kind of go along with this, a handy-dandy little theorem. And it's going to say if a sequence, and we're going to call our sequence a sub n, is bounded, remember that means above and below, and monotonic, then we can say, then we know that a sub n converges. And sometimes our our theorems are kind of duh statements, but this is what this means, and then we can use that information for later. Alrighty, so I just have a couple of examples that I want to show, and then we will be done for today. So the first example, I'm going to have a sub n is equal to, oops, I forgot the other side, 1 over n. Okay, so this particular sequence is going to be, if you think about 1 over n, it's bounded and monotonic. Okay, so it is a bound above by 1, and it's bound below by 0. Okay, and if you think about what that sequence might look like, this particular function is strictly decreasing. And so then we would say, oops, my paper got stuck. We would say that this particular function converges, and then it happens to converge to 0. Okay? All right, for my next example, oops, sorry. I think I need some more coffee. I'm going to have the sequence b of n is equal to, and then I'm going to have n squared over n plus 1. Okay? This one is monotonic. And remember that if you're unsure, you could put this in your calculator. You could put your calculator in sequence mode, and then you could put this in. You could put in an n as 1 or 0, and then you could look at the graph of your sequence. And remember, it is a collection of individual points, not a continuous function. This one would happen to be increasing. Okay, and then we would say it is bound below. It is not bound above, because if you'll notice, if my n was 0, the smallest value that my denominator is going to be is 1, but the the top is going to grow, the numerator, without bound, so it's not bound above. Okay, and then I have one last example before we start doing some classwork. And this particular rule, this particular sequence is going to be a -1 raised to the n. Well, if you'll notice, all this does, if you think about it, so if I have, this is a sub 1, a sub 2, a sub 3, the first one might be here, the second one would be here. I lied, they would switch places. So I'm going to put an X and an X. This guy's going to be here, this guy's going to be here, because if n is odd, then it's negative, and then if n is positive, then my sequence value is positive. This is going to oscillate between a -1 and a positive 1, so it's an oscillating function. The other thing that we know about this one is that it is bounded, which means that it is bound above and bound below. So it is bound above by a positive 1. It is bound below by a -1. But this one is not monotonic. Therefore, this particular sequence diverges. Alrighty, that is it for today. I will see you tomorrow.